So guys, in this video, soon after we have seen the extraction of the iron from iron oxide. In this video, we are going to see the extraction of the copper from the copper pyrites, that is your Cu2s. That is, we can say a sulfide ore of your copper. But the main thing I want to involve over here is, of course, whenever we are doing the extraction of any metal from its corresponding oxide, always the question arises that what will be the reducing agent we are going to choose? True. And in order to answer for the selection of your reducing agent, we know that it will be only be answered by seeing your Ellingham diagram. So coming with respect to your Ellingham diagram, we can just see here, yes, in the Ellingham diagram, when compared to the other metal to metal oxide curve, the curve of your copper is lying almost at the top. That's the thing. So according to the characteristic of your Ellingham diagram, the curve for the other metals which is lying below the curve of your metal oxide, those curves, any of the metal or the element can be taken as that of your reducing agent. But of course, I have mentioned you, these are all the commercial parts. So we have to choose a reducing agent which will be easily available for us and also which will be very cheap for us. So by that way, I am going to choose that of your coke as a reducing agent here once again. But when just recalling the part of your iron to iron oxide, I have maintained a temperature of nearly greater than 1073 Kelvin. But when we are seeing the curve of your copper and that of your carbon, of course, the carbon to carbon monoxide curve is lying below that of your copper to copper oxide curve in the range of nearly greater than that of your 500 to 600 Kelvin. So if I am maintaining only that little temperature, of course it will be beneficial for the industries and also it will be economically very useful. So whatever the extraction of the copper is done over here is by using a reducing agent through an Ellingham diagram we have seen, that is your coke, because it is commercially available in a cheaper cost and also easily available. So coming with respect to what we are doing in this, of course, the main reaction, whatever we are doing as a reducing agent, first and the foremost thing we have to understand that once the ore has been extracted from the earth, it has been concentrated with respect to that of your froth flotation. Alva. So remember, froth flotation is mainly employed for that of your sulfide ores. So first and the foremost thing, in order to remove certain sand or mud particles, first the ore is subjected to that of your froth flotation. Once it has been concentrated, what will be the next step? Of course, we are going to burn those ores in order to convert their respective oxides. Now, can I ask you a question? Of course, there is a hint in me. Why we are converting them to respective oxides? Because once they are converted to the respective oxide, from that data itself, the Ellingham diagram can be chosen. If you can just see, all the metals to their metal oxides ka Ellingham diagram we are having. That is the reason we are converting whatever the composition of your ore may be. First, we will be converting them to their respective oxides. So after the froth flotation, we are going to burn your ores. Since it is a sulfide ore, which process you are going to take? Of course, roasting. That is what? In the presence of air. Able to understand? So once you have done the roasting process, the next process is called as that of your reduction or that of your smelting. That is, you are going to heat your ores in the presence of that of your suitable reducing agent. If I come to the main part of the reaction, of course what we are going to do is, so whatever the Cu2s is there, that is going to burn in the presence of oxygen. Yes, you will be getting a Cu2O plus that of your SO2, and this Cu2O plus that of your coke, whatever you have chosen as a reducing agent, the reduction of your metal oxide takes place to give you that of your copper plus that of your carbon monoxide. But actually we have to remember that whatever the reaction we have written initially, it is not that much simple which is taking place in an apparatus which is called as that of your reverberatory furnace. So what is happening over here? Basically in the reverberatory furnace, of course we have taken an ore of your copper. But most important thing we have to remember that whatever the ore we have taken of the copper, it is having a composition of your. So whatever the ore we have chosen, it is having the composition. That is initially what we have dug from the ore, it is of your copper pyrite, that is CuFeS2. That is your copper is also having a quantity of your iron. But in this case what will be happening, your iron will be acting as an impurity. So in our later case, that is your earlier session, we have seen that in order to remove the impurities from the iron ore, we choose limestone as a flux. And I have mentioned you, flux will be changing with respect to the extraction of the metals. Different metals, different flux could be used. So in this case, whatever the reduction part of your copper is taken place, in this case we are using a flux called as that of your silicate. This silicate, what it is trying to do is, whatever the iron part is there, that is going to react with the silicate to form your iron silicate. That is, of course, whatever the once you are done, because here I am just shown as copper sulfide, but this copper sulfide is actually in the form of CuFeS2. So when you are undergoing an oxidation, of course you are getting your copper oxide. Along with that one, you will be also getting your iron oxide. So that will be also treated with that of your flux silicate to give respect to that of your slag of iron silicate. So this is your gangue, that is your impurity. This is your flux. Here is a silicate. And whatever you have obtained a fusible material, this is called as slag. But do remember guys, of course in the part of your blast furnace of your extraction of the iron, we got to know that whatever the iron we are getting, it is not the purest to form. That was called as a pig iron. Similarly over here, though we have used and removed the impurities of the iron, but the copper what we are obtained from that of your reverberatory furnace, the last stage will be in a composition of Cu2s plus Fes. So that copper will not just be a copper, it will be also having the sulfide and also another impurity of your iron sulfide. So in a reverberatory furnace, whatever the copper part you are getting, it is called as copper matte. Very much important. You can be asked, what is the composition of your copper matte? So you have to remember that the composition of your copper matte is that of your cuprous sulfide and that of your ferrous sulfide. There may also a question that what will be the oxidation state over here guys? Of course, it is having an oxidation of your copper as +1. That is the reason I am saying it as a cuprous sulfide. Yes. So now the thing arises that of course after doing whatever the analysis, the reduction part using your coke, the last stage from the reverberatory furnace we are getting as a composition of the copper as copper matte. So now what we are going to do is, now this copper matte is taken in that of your decimeter, or once again a different instrument. So in this decimeter what you are going to do is similar to that of your furnace itself. We are going to blast a hot air in it. So of course what happens, whatever your Fes is there in this copper matte will be first gets converted to that of your respective iron oxide plus your SO2. Yes. Then the question arises, whatever this iron oxide is there, so in this decimeter once again we have added silica as a flux. So added silica as a flux, what it is going to do, it is going to get reacting with that of your SiO2 to give respect to that of your slag. So whatever the copper matte we have obtained, from that part we have completely removed that of your iron impurities, which has been come out as that of your slag of iron silicate. Now the question arises how to convert this Cu2s to Cu. So when you're blasting the hot air in that decimeter converter, part of your Cu2s gets converted to that of your cuprous oxide plus SO2. Since the part of the cuprous oxide, Cu2O, sorry, is then this Cu2O once again reacts with the remaining part of your Cu2s to give you Cu plus SO2. That is your 6Cu part you are going to get if I am going to balance. Yes. So this is the part in the final stage, whatever you are obtained, that will be in the purest form of the copper. This process can be also called as that of your Bessemerization process. Bessemerization process. Since it is done in a Bessemer converter belt or a Bessemer converter. Bessemerization process mein we are getting the purest copper. But the question arises over here that whatever the copper we have obtained over here, it is called as blister copper. Of course, you may be knowing the word as blister. That is, if I take this one as was your copper, it will be having certain holes on top of it. That is the reason it is called as blister copper. Why we are obtaining these pores? It is mainly because you could just see that whatever the SO2, a byproduct we have obtained in this reaction, that is in the gaseous form. This copper is getting solidified. During the solidification of the copper, this SO2 gas has been evolved out through this pores, leaving back the origin of its evolution. That is the reason we are calling whatever the copper we have obtained at the Bessemerization process, it will be called as that of your blister copper. So by this way, one can easily extract the copper from a copper pyrites. But do remember, major important thing. So during the extraction of the copper from copper pyrites, we have seen that the first part is you have used the silicate as a flux. Yes. Whereas you have used coke as your reducing agent. Temperature you have maintained nearly 500 to 600 Kelvin. Yes. And whatever the copper you have been obtained in a reverberatory furnace, that is not the purest copper. Instead, it is in the form of your copper matte. That is, you are having the composition of Cu2s plus FeS. Then the Cu2s and FeS, once again it is treated in a Bessemer converter along with the silica as a flux, where your iron impurities are getting oxidized and treated with the top of your silicate flux to get as iron silicate as a slag, which has been removed easily. Then the remaining copper sulfide on oxidation gives you the cuprous oxide. That cuprous oxide reacts with that of your remaining cuprous sulfide to give you the copper. So whatever the copper we have obtained in a Bessemer converter, that is in the form of your blister copper. That is similar to that of your bread. So when you are seeing the bread, we could just see that certain pores on them, holes on them. What are those holes? It is mainly indicating the path of your evolution of CO2 in your bread, because the baking soda, whatever we are using for the manufacture of the bread. So when you are heating those bread, CO2 will be evolved, leaving back the holes. But in this process, whatever the copper we have obtained, it is having the blisters, which is indicating the evolution of your SO2 gas. And that is the reason it is called as that of your blister copper. Coming to the last part of your this process, of course, it is the extraction of the zinc from zinc oxide. Of course, the reduction of the zinc oxide is also done using your coke. The temperature in this case is higher than that of your, what you can say, copper. Of course, you could see over here in the Ellingham diagram. Of course, we are using the coke itself, but what is happening? The curve of zinc to zinc oxide should lie above, and once it is lying below that of your coke, yes, the coke curve should lie below that of your zinc oxide curve, and that is happening only at nearly, we can say, the temperature range of 1073 Kelvin. Yes, so it is greater than that of your copper part, but also we are using for coke as itself as a reducing agent. So what is doing? For the purpose of heating, the oxide is made into briquettes. That is like a small powder like material with coke and a clay. You are going to mix it thoroughly. Of course, in that furnace itself, what happens? ZnO plus C, coke, nearly you have taken coke 1673 Kelvin. So you'll be getting your zinc plus that of your CO. So whatever the zinc you're getting over here, it is nearly in the molten form. So therefore the metal is distilled off, and once you have been distilling this metal, it is undergone a rapid chilling. Rapid chilling means you're going to freeze it rapidly. And during that process, what happens? The metal gets solidified and easily you can take back your zinc. Compared to that of your copper and iron, zinc is somewhat easier part. So that is the reason I have included the zinc part in this video itself, since it's a small concept. So of course we are using the coke itself over here as a reducing agent. So extracting the zinc at the temperature that of your 1673 Kelvin. But remember that the metal is first distilled off and then it is collected by rapid chilling. So guys, in our two videos we have seen that we have extracted the iron from iron oxide, where we have maintained a temperature of greater than 1073 Kelvin. We have used coke as our reducing agent, yes, and we have used limestone as a flux, very much important. But in the next part we have seen from your copper, we have extracted from that of your copper sulfide, maintaining a temperature of nearly 500 to 600 Kelvin. Here we have also used coke as a reducing agent, yes, but what is the main difference? We have used silica as that of your flux. So in this case, what the slag we have obtained is that of your calcium silicate. CaSiO3 was a slag. But here, what is the slag we have used? Whatever the slag we have got, of course, it will be your iron silicate. Very much important for 1 marks. They can ask you anything. So you should be very much aware whenever you are reading these topics. So in copper, whatever the extraction of the copper is including, that is having a slag of iron silicate. In the extraction of the iron, we are having the slag of calcium silicate. Coming with respect to the zinc, of course, here from zinc oxide, we have extracted the zinc. Yes, I should use in this way arrow mark. Thanks for that. So in this way, you have to write your arrow mark. That is, from iron oxide, we have obtained iron. From copper sulfide, we have obtained copper. From zinc oxide, we have obtained zinc. So here we are nearly maintaining a temperature of 1673 Kelvin. And of course, here also we are using the coke as a reducing agent. But what we are doing is, first of all, the metal is distilled off. Metal is distilled off. And then the metal is obtained by rapid chilling. That is rapid freezing. So if you make a kind note over here, whatever the extraction we have done from the respective ores is by maintaining a suitable temperature and by using a suitable reducing agent. Remember guys, whatever this process is including by maintaining a temperature and using a suitable reducing agent, this methods in metallurgy is called as pyrometallurgy. Pyrometallurgy. If I want to give it a complete proper definition, we can say that it's a process of extraction of a metal. Process of extraction of metal. Yes. In a molten state. In a molten state. Molten state means nothing. Semi-solid anta. In a molten state, by heating the roasted or calcined temperature. By heating the roasted or calcined ore. Okay, by heating the extraction of the metal in a molten state, by heating the roasted or calcined ore at a high temperature, and using a suitable reducing agent. Using a suitable reducing agent. What we have explained, just the proper definition. So it's a process. Once again I am saying, so it's a process of extraction of a metal in a molten state by heating the roasted or calcined ore. So whatever the ore we were taking, of course they have been undergone the suitable roasting or that of your calcination process. So from that one we are going to extract the metal. How? By maintaining a high temperature and using a suitable reducing agent. So all these three extraction of the metals, that is from iron oxide, iron, copper sulfide, say copper, zinc oxide, say zinc, this process is called as pyrometallurgy. Why I am saying this is because the next extraction which we are going to see in our next video is involving the extraction of your iron from that of your bauxite. So this is undergoing with respect to that of your electrometallurgy. Of course, you can able to understand. So whatever we are going to use is with respect to the electricity. That is the reason it is very much important to understand the difference. So this was the case of your pyrometallurgy, where we have extracted the metals by using a suitable temperature and that of your suitable reducing agent. And in electrometallurgy, what we are going to do is we are going to extract the metal depending upon the electrode potentials of the metals by using your electricity. That is the reason. And also we are also having a one more method which is called as that of your reduction oxidation method, which is another class of your extraction of the metals, which would be seen in our later class. So with one each, we have to understand what are the difference. So in pyrometallurgy, we are maintaining a suitable temperature and selecting a suitable reducing agent. In electrometallurgy, we are making use of electricity and that of your electrodes, which will be seen later in later videos. In reduction oxidation is a general reaction itself. Of course, I can give you an example, the leaching of gold, whatever we have done. It is mainly involving that of your oxidation reduction process, which will be dealt in a very conceptive way in my later videos.